So imagine trying to perform a biopsy deep inside a highly confined space in the human body. Something incredibly narrow, like a bile duct.
Right, which is just a notoriously difficult environment to navigate.
Exactly. I mean, standard biopsy forceps are massive for this kind of work, usually coming in around like 2.3 millimeters wide.
Yeah, way too bulky.
Right. Now, picture replacing those bulky metal forceps with a fully functional three-dimensional microgripper that is literally thinner than an ant's jaw.
Wow.
And it's seamlessly integrated directly onto the tip of a single optical fiber. Welcome to the 2PP podcast.
Thanks. I'm really excited for this deep dive.
Yeah, me too. Today, for all of you listening, we are unpacking a really fascinating recent paper detailing the creation of a 3D optical fiber gripper, or OFG.
Right. And, for those of us spending our days optimizing voxel spacing and tuning femtosecond lasers, the actual printing process itself is fairly familiar territory.
Oh, for sure. We all know how 2PP works.
Yeah. But the mission today is to examine the engineering mechanics behind this device. Specifically, how the researchers navigated the multi-material integration.
Because that's the tricky part, right?
Exactly. And what this means for deploying two-photon polymerization out of the lab and into, real-world dynamic environments.
Right, out into the wild. Because the transition from static substrate-bound microstructures to active fiber-integrated robotics is, well, it's a massive hurdle in our field.
It really is. What stands out to me in this architecture is the intentional targeting of an intermediate force regime.
Okay, let's unpack that a bit.
Sure. So historically, the manipulation landscape at the microscale has been heavily polarized. You have optical tweezers, which offer incredible sub-micron precision. Right.
But they rely on the momentum transfer of photons.
Exactly, meaning they generate very weak optical trapping forces. We're talking typically in the piconewton range.
Which really limits you to highly specific, mostly transparent targets.
Spot on. And then, on the flip side, you have millimeter-scale mechanical tweezers.
Which are huge.
Yeah, I mean, they offer the necessary micronewton forces, but they completely lack the spatial resolution for subcellular work.
So the OFG is engineered specifically to, occupy that missing middle ground.
Exactly. It's the perfect bridge.
So to understand how they achieved that force profile, we first have to look at the structural foundation.
Right.
They built this directly onto the cleaved facet of a multimode optical fiber. And the overall dimensions are just microscopic, 38 by 38 by 61 cubic microns.
Which is tiny. And choosing a multimode fiber, specifically one with a 50-micron core and a 125-micron cladding. I mean, that isn't an accident.
No, not at all. That 50-micron core acts as the perfect spatial envelope for delivering the actuation energy directly into the base of the gripper.
Right, without having to rely on external wiring or, complex microfluidic channels.
It's all self-contained?
Yeah. Building on that cleaved facet inherently transforms the fiber from a passive light guide into the primary energy delivery channel.
But doing that, I mean, the structural engineering required to make a functioning gripper at that scale demands two fundamentally conflicting mechanical properties, right?
Absolutely. You need a really high elastic modulus and rigidity to physically shear and grasp the target.
Like the bone?
Exactly, the bone. But you also need extreme elasticity and volume responsiveness to drive the actuation, like a muscle.
And you just can't get both from a monolithic structure printed from a single photoresist.
No, you really can't, which is why they utilized a two-step multi-material 2PP process.
Okay, so step one involved printing the rigid skeleton using SC2080 photoresist. And they went with a 3-arm microclaw design.
Right. And then in step two, they moved to the contractile element, printing a soft thermoresponsive hydrogel.
Doped with silver nanoparticles, right?
Yes, doped with silver nanoparticles precisely inside the interior volume of those claws.
No, wait. Why a 3-claw architecture? Why not 2 or 4?
Well, what's fascinating here is that it's an exercise in microkinematics. A 2-claw design is inherently unstable when dealing with asymmetrical or spherical objects.
Oh, because the target tends to just slip out along the unconstrained axis.
Exactly. It just slides right out.
Yeah.
But a 4-claw design, on the other hand, creates an over-constrained hyperstatic system.
Which means what exactly at that scale?
Well, at the microscale, if your laser alignment drifts even slightly during the print,
Oh, right.
or if the hydrogel swelling is marginally non-uniform, one claw of a 4-claw system will engage before the others.
And that completely ruins the grip.
Exactly. It throws the whole thing off. But 3 points define a plane. A three-claw design is self-centering and kinematically stable.
which drastically reduces the margin of error required during the fabrication and alignment of the two separate materials.
Exactly. And that kinematic stability is crucial when you look at the interface between the SC2080 and the hydrogel.
Right, because they printed that hydrogel muscle using a voxel spacing of 400 nanometers at 20 milliwatts of laser power.
And for anyone listening who has tried to print multiple materials sequentially, delamination is the primary mode of failure.
It just peels right apart.
Yeah. But at 400 nanometer spacing, you aren't just optimizing for print speed, you are intentionally leaving a specific degree of surface roughness on the SC2080 boundary.
Oh, I see. So that topography provides the mechanical interlocking necessary for the hydrogel to anchor itself to the rigid skeleton.
Spot on. If the interface is too smooth, the shear forces during actuation will simply peel the hydrogel away from the photoresist.
So we have this beautifully printed composite structure on a fiber, but how do we actually make the muscle flex without moving parts?
That's where the localized actuation mechanism comes in. It relies entirely on those silver nanoparticles embedded within the hydrogel matrix.
Okay.
When an 808 nanometer near-infrared laser is fired down the multimode fiber, it hits the base of the gripper.
And the silver nanoparticles are highly efficient photothermal converters, right?
Exactly. They absorb that 808 nanometer light and rapidly convert it into localized heat.
And the thermodynamics of the hydrogel's response are honestly incredibly elegant here.
Oh, they really are.
Like, in its resting state, at ambient room temperature, the polymer network of the hydrogel is highly hydrated, right? Stabilized by hydrogen bonds with the surrounding water molecules.
Right, so the hydrogel is physically swollen, and that osmotic volume expansion is what pushes against the rigid SE2080 claws.
Keeping them mechanically clamped shut.
Exactly. The default state is a closed grip.
Okay, so then the moment the silver nanoparticles generate heat, the localized temperature of the hydrogel crosses its lower critical solution temperature, or LCST.
Right, and crossing that thermodynamic threshold breaks the hydrogen bonds between the polymer chains and the water molecules.
The polymer chains suddenly prefer to bond with each other rather than the water?
Yes, so the hydrogel violently expels the water, undergoing this massive volume phase transition. It shrinks rapidly.
And because it is anchored to the interior of the skeleton, that volumetric contraction pulls the claws open?
Exactly.
Yeah.
Cut the laser power, the localized heat dissipates, the polymer network rehydrates, swells, and the claws snap back shut.
But wait, phase transitions in thermoresponsive hydrogels are notoriously sluggish, right? Like, often taking seconds to fully cycle because they rely on the diffusion of water?
Normally, yes.
Mm.
But because we are operating at a scale of tens of microns, the surface area to volume ratio is massive.
Oh, which allows for incredibly rapid diffusion and thermal dissipation.
Precisely. The OFG reacts in just 76.7 milliseconds to reach 75% of its maximum opening stroke.
That is so fast.
And it can be driven continuously at frequencies up to 5 Hz.
And what about endurance? I mean, 5 hertz is a lot of mechanical stress.
Well, the fatigue resistance really highlights the integrity of that 400 nanometer mechanical interlocking we talked about. They ran a continuous fatigue test, cycling the OFG over 87,000 times over a 48-hour period.
87,000 cycles.
Yeah. And there was no measurable degradation in performance, no delamination at the material interface, and no thermal degradation of the polymer network.
That's wild. I guess because the silver nanoparticle doping is localized precisely where the heat is needed, preventing the broader SC2080 structure from experiencing continuous thermal shock.
Exactly. But honestly, the raw mechanical output is what genuinely redefines the capabilities of fiber-integrated actuators.
Oh yeah, the mass-to-force ratio is insane. The entire gripper weighs only 14.3 nanograms.
Right.
Yet they demonstrated it lifting a 20-centimeter long, 20-micron thick, solid copper wire.
Which requires a lifting force of 4.9 micronewtons.
So we are looking at a force-to-mass ratio of roughly 340 micronewtons per milligram.
Right. For a soft material microactuator, generating that kind of normal force against a target is just unprecedented.
But wait, pushback here. If we are pumping near-infrared laser energy into a highly confined space to rapidly expel water from a hydrogel, aren't we going to fry whatever we are trying to grab?
It's a very valid concern.
Mm-hmm.
It introduces a massive risk of severe thermal damage, especially if the intended target is live biological tissue or a single cell. But the thermal operating window of this specific hydrogel formulation handles that beautifully. You don't need to elevate the temperature dramatically to trigger the phase transition.
The LCST of this network falls within a physiological range, doesn't it?
Exactly.
Yeah.
We aren't boiling the surrounding fluid. We're merely shifting the thermodynamic equilibrium of the polymer chains just above body temperature.
Oh, wow. Okay.
Furthermore, because the silver nanoparticles are so efficient at absorbing the 808 nanometer wavelength, the required laser power is remarkably low,
Like how low?
scaling down to 6 to 8 milliwatts depending on the doping density.
So that near total absorption means there is virtually zero laser leakage propagating past the hydrogel and striking the target object.
Exactly. The heat generation is strictly confined to the interior boundary of the claws, leaving the target specimen entirely within a safe thermal envelope.
Okay, so knowing that the thermal profile is safe and the mechanical force is immense, let's talk about physical manipulation.
Sure.
Because traditional optical tweezers fail when introduced to opaque materials, right?
Yeah, or objects with high refractive indices,
Uh-huh.
because they depend on manipulating the momentum of light passing through the object. If the light can't pass through predictably, the trap just fails.
Right. But the OFG bypasses optical constraints entirely by relying on physical Coulomb friction, like an actual tiny hand.
Exactly. And they demonstrated this by effortlessly grasping opaque aluminous spheres ranging from 9 to 24 microns in diameter.
And the reliance on physical friction also allows for the handling of highly irregular geometries, right? Which are normally a nightmare to stabilize in optical or acoustic traps.
Oh, they're notoriously difficult. But the researchers successfully captured and reoriented jagged silicon carbide microfragments, polymer microrings, and complex micropentagonal stars.
Just because the three claws can conform to the asymmetry of the object?
Right. They utilized the restorative swelling force of the hydrogel to maintain continuous surface friction.
Here's where it gets really interesting to me. They took this geometric freedom and moved directly into programmable 3D microassembly.
Yeah, that was a huge step.
Like, they didn't just slide objects around a flat 2D focal plane on a glass slide. They picked up silica spheres, arranged them into a precise 1 by 3 grid to spell out AHU in binary code, and then moved into the Z-axis.
Right, like playing with microscopic arcade claw machines to build 3D scaffolding.
Exactly. They stacked individual spheres at highly specific vertical elevations, 0, 20, and 40 microns above the substrate.
And that vertical lifting capability is a direct result of the clamping pressure. Using a custom on-chip microspring force sensor, the empirical data showed each claw exerts approximately 2.2 micronewtons of force.
Which is significant.
Yeah. In the realm of microelectromechanical systems, or MEMS, that specific force profile acts like a microscale cullet chuck.
So it generates enough distributed frictional holding power to counteract gravity and local fluidic drag.
Exactly, allowing the operator to translate heavy, opaque objects vertically through the fluid without dropping them.
But wait, friction and clamping pressure are perfect for lifting solid copper wire or silica spheres. But what about when you need to grab something squishy, fragile, and alive?
Right, like a lipid bilayer.
Yeah. Biological cells are incredibly soft, heavily susceptible to shear stress, and easily ruptured by continuous mechanical pressure. I mean, applying 2.2 micronewtons of force directly to a cell membrane usually results in instant lysis, right?
Usually, yes. The cell would just burst. But the solution to the biological handling challenge lies in the continuous analog nature of the photothermal actuation.
Okay, so it's not just an on-off switch.
Exactly. The OFG is not a binary open or shut mechanism. The volume phase transition of the hydrogel is directly proportional to the applied thermal energy.
So by continuously modulating the laser power, say, maintaining it precisely at 15 milliwatts instead of fully powering off to 0, the operator can maintain the hydrogel in a state of partial contraction.
Exactly. It's this grayscale control.
Like a dimmer switch instead of just a simple on-off light switch.
Perfect analogy. It allows the user to actively counterbalance the elastic restoring force of the hydrogel network. You don't let the claws snap shut with their maximum pressure.
You tune the laser to offset that pressure, applying just a fraction of a micronewton. It operates like a programmable servo actuator holding a fragile object, like holding a water balloon.
Yes, you dial in the exact tension required to establish friction without penetrating the membrane. The researchers proved this by manipulating single HeLa cells, 3T3 fibroblasts, thyroid cells, and CACO2 colorectal cells.
And the viability metrics post-manipulation confirm how gentle that grayscale control really is.
We do. After capturing a single suspended HeLa cell, transferring it through the fluid, and releasing it at a target location, the cell was subjected to a 4-hour incubation period.
And what was the survival rate?
98.7% of the manipulated cells not only survived, but actively spread out, adhered to the new substrate, and continued to divide normally.
Wow. So the operators could control the exact physical deformation of the cell during transport without causing any structural damage.
Exactly. And they pushed the complexity even further by demonstrating cooperative manipulation, using two independently controlled OFGs simultaneously.
Two of them at once.
Yeah. They positioned one OFG to gently grasp and anchor a large multicellular cluster. Then, they brought in the second OFG, targeted a single cell on the periphery of that cluster, and carefully peeled it away while the first OFG kept the main body stationary.
That is just incredible. I mean, the implications for biomedical engineering and single-cell sequencing are profound.
If we connect this to the bigger picture, it really is. The standard laboratory protocols for isolating a single cell from a cluster typically involve bulk fluidic shearing or the introduction of enzymatic agents like trypsin.
Which degrades the cell-to-cell adhesion proteins.
Right. And both of those methods fundamentally alter the mechanical state, the transcriptomic profile, and the surface chemistry of the cell.
So the ability to mechanically isolate a single cell non-destructively without chemical intervention preserves the cell in its native state for downstream hemolysis.
Exactly. It also allows us to deliberately populate custom 2pp printed 3D microscaffolds cell by cell, creating highly controlled artificial microenvironments to study cell migration and differentiation.
Well, all of this precision work on the lab bench perfectly sets up the ultimate test. Returning to the dream scenario we introduced at the very beginning of the deep dive.
Operating inside the human body.
Exactly. Because the entire premise of building this on the facet of a 125-micron optical fiber is to gain access to anatomy that traditional tools simply cannot reach.
Right. The spatial constraints of the human vascular or biliary system require unparalleled miniaturization. So to simulate this, they first subjected the OFG to a highly constrained artificial environment.
They navigated the fiber through a glass capillary tube, right? Measuring 13 millimeters in length with an inner diameter of only 300 microns.
Very narrow, and the device successfully traveled the length of the capillary, actuated, captured a microscopic target, and withdrew safely.
And then they escalated to an ex vivo biological model, deploying the OFG into a freshly excised rabbit bile duct.
Right. They utilized a standard stainless steel medical catheter with an outer diameter of 0.51 millimeters to act as a protective sheath during navigation.
The fiber was fed down through the catheter until the tip made contact with the mucosal lining of the duct. And the procedure here showcases the absolute necessity of the multi-material architecture.
It really does. Because a soft hydrogel alone cannot penetrate or tear tissue.
And a rigid photoresist alone cannot maintain a continuous dynamic grip.
Right. So the researchers fired the laser to open the claws, advance the skeleton into the tissue, and cut the laser power.
And as the hydrogel swelled and clamped down, the rigid SC2080 claws provided the necessary shear edges to bite into the tissue.
While the continuous osmotic pressure of the hydrogel maintained the normal force required to pull the sample free as the fiber was retracted.
So what does this all mean? The successful extraction of that tissue sample from inside a bile duct proves that this technology is no longer theoretical.
Exactly.
I mean, by scaling down the intervention tool by a factor of 20 compared to traditional biopsy forceps, we are looking at the future of minimally invasive microsurgery. Entirely new regions of the human anatomy become accessible.
And what accelerates the translational viability of this specific design is the foundation itself. By integrating the microgripper directly onto a standard multimode optical fiber, the researchers ensured inherent compatibility with existing clinical infrastructure.
Right, because optical fibers are already the backbone of modern endoscopic systems, optical coherence tomography, and robotic surgical platforms.
Exactly. The researchers didn't invent some proprietary siloed platform. They leveraged existing clinical hardware and simply replaced the macroscopic end effector with a 2pp printed active mechanism.
It takes 2pp from a stationary lab manufacturing process and turns it into a deployable medical intervention tool.
It forces a massive reevaluation of what multiphoton lithography can achieve. We are no longer limited to printing passive structural geometries. We are printing integrated, active thermodynamic engines and kinematic linkages at the microscale.
So, to summarize this incredible journal, by utilizing two-step 2pp, researchers created an ultra-compact, fast, and strong microgripper that seamlessly integrates a rigid photoresist skeleton with a soft hydrogel muscle.
Representing a massive leap forward in manipulating everything from complex micromachinery to living cells and internal biological tissues.
For all you 2PP experts listening, the boundaries of what you can print are no longer confined to static microstructures on glass slides. You are printing active, deployable robotic systems.
And I'll leave you with a final, lingering thought to mull over on your own. If we can use 2PP to print silver-doped hydrogel muscles and photoresist skeletons on a fiber tip to act as a hand, what happens when we start using multiphoton lithography to print other organs?
Wait, really? Like what?
Well, could we print integrated optical sensors or fluidic pumps onto the very same fiber tip, creating a fully autonomous microscopic robotic surgeon?
That doesn't just grab tissue blindly, but analyzes its chemistry in real time before extracting it.
Exactly, making diagnostic decisions continuously before the extraction even occurs. The engineering principles demonstrated here provide the exact foundational mechanics required to make that level of integrated remote microrobotics a reality.
A microscopic robotic surgeon, thinner than an ant's jaw, performing targeted, real-time chemical analysis and mechanical extraction deep inside a bile duct. The frontier of 2PP is moving incredibly fast. Thank you for joining us on this deep dive.